Hello everybody and welcome to today's lesson on graphing exponential functions and applications. This is the first lesson in our unit on exponential and logarithmic functions, and today our objectives are we will graph exponential functions using a transformational approach, and we will use exponential functions for practical applications. So let's first talk about what is an exponential function. An exponential function is a function where x, our input variable, is itself in the exponent of that function. And what that means is that, of course, we're going to have a base, and the base is usually abbreviated by b. So b to the power of x. X is our input variable and is in the exponent. B has to be a number which is greater than 0. It also cannot be equal to 1, because remember, 1 to any power whatsoever is always 1. So what would be the point of having a function if the output is always 1, right? And x has to be a real number. So how do we evaluate an exponential function? In other words, how do we find output values for that function? We just take our input value, our x, and put it into the function, and then go ahead and evaluate. Like in this example, f of x is equal to 3 to the power of x. F of 2 then would be 3. That doesn't change. That's our base. To the power of 2, or 3 squared, and that is of course equal to 9. Or for example, f of negative 4 for that same function, 3 to the power of x, would be 3 to the power of negative 4. And now we have a negative exponent, and remember what happens when we have a negative exponent. We need to take that term and flip it into the denominator of a fraction. So 1 over 3 to the power of 4, and 3 to the power of 4 is, of course, 81. When we want to graph an exponential function, we need to find our key points first again, and that is going to make things so much easier. And we can find key points even for a general exponential function, just like b to the power of x. Remember, we said b, that stands for our base, and that can be different numbers. But even without knowing what b is, if we plug in these numbers, negative 1, 0, and 1 in for x, what are we going to get? b to the power of negative 1, just like above. Remember, negative exponents, take that term and put it into the denominator, and that would be 1 over b. b to the power of 0. It's also a pretty important one, but at the same time easy to remember. Anything to the power of 0 is always 1. And b to the power of 1 is just basically b itself. Let me also transfer that here into our table of key points. So keep those key points in mind and always refer back to them, and then everything else from there we do using our transformational approach. So then let's go and graph our first example here. F of x is 2 to the power of x, so 2 is our base, and that means for our table of values, if x is negative 1, 2 to the negative 1 is 1 over 2. 2 to the 0th power is 1, as any other number would be as well. And 2 to the first power is just itself. And here we have our first 3 key values. So we can go ahead and graph our function. Let me first put our coordinate plane in. If x is negative 1, y is 1/2. If x is 0, y is 1. If x is 1, y is 2. and from there it goes on up really fast. It grows exponentially. And I'm sure you have heard this expression in another context before, and that's really where it comes from. This is what our curve will look like, and on the left, it will never actually touch or cross the x-axis, and that is because no matter how small and how negative our x input gets, that will never turn our term negative. All it'll do is it'll put that term into the denominator, and the fraction will get smaller and smaller and smaller. On the right, our curve will grow very fast, and you know that already from our quadratic and from our cubic functions. With exponents, the functions grow very fast. So what can we say about our domain? The domain is x such that x is an element of the real numbers. It goes from negative infinity all the way to positive infinity. The range, however, is a little different. The range will not go lower than 0. It will not even touch 0. And shown in interval notation, that would be parentheses 0, comma, infinity. It does go to positive infinity. And we do have an asymptote precisely because we don't touch the x-axis or cross it. We have an asymptote, and that asymptote is y is equal to 0. And now let's talk about our end behavior. As x goes to negative infinity, f of x will go to 0. And as x goes to positive infinity, f of x will also go to positive infinity. And when we have a function like this that grows towards the right, we talk about a growth function. Then let's look at our next example. Here we have a base of 1/2. So that's going to change things a little bit. 1/2 to the power of x, if that is -1, we need to flip the term, and then we get 2 over 1, or just simply 2. 1/2 to the power of 0 is 1, and 1/2 to the power of 1 just stays itself. And then we can again graph this in our coordinate plane. Where x is -1, we get y is equal to 2. At 0, it is 1. And at 1, it is 1/2. And this one will actually look like this, coming from negative infinity and going all the way towards the right, getting closer and closer to the x-axis, and yet again never touching or crossing it. And that is because we said our output can never turn negative no matter what we put in for x as an exponent. So that means our domain goes from, and now I'm going to do it in interval notation, negative infinity to infinity. And our range again will not include 0, but start right after that, and will go to positive infinity. We do again have an asymptote, and the asymptote is at y is equal to 0. And our end behavior, as x goes to negative infinity, f of x goes to infinity, and as x goes to infinity, f of x goes to 0. When we have a function like that, where the y values, the outputs come from really, really large numbers and get small really fast and then get smaller and smaller and smaller, we call this a decay function, because the y gets smaller and gets almost to 0, never quite reaches it though. And so what's the difference between a growth function and a decay function? What determines the shape of that? And that is, if we look at our base, and that's really the determining factor here, if the base is greater than 1, we will have a growth function. But if the base is between 0 and 1, remember it cannot be 0 and it cannot be 1, but then we will have a decay function. So what would the graph of an exponential function look like if we had a little bit more going on here, like in these two examples that we have here on the next page? Well, then we're going to use our transformational approach that we have been using before in many other cases. And for that, let's just remember that we have f of x, which is equal to a times b to the power of x minus h and plus k. So that's the general form where we have our a and our h and our k. And remember, a is the dilation, h is the horizontal shift, and k is the vertical shift. So let's get our key points first using the given base and then do our transformations afterwards. The base here is 2. So our key points are 2 to the power of negative 1 is 1/2. Just flip your number. 2 over 1 gets flipped into 1/2. 2 to the power of 0 is 1, and 2 to the power of 1 is itself. We had these numbers just a few moments ago. And we're going to graph these points first and then take it from there step by step. -1, 1/2, 0, 1, 1, 2. Those would be the points if we only were concerned about our base. Now we need to talk about dilution. Dilution is 1/2, and that means that each of our y values, each of our outputs, is going to be just half as large as it should be. So 1/2 times 1/2 is going to be 1/4. 1 times 1/2 is 1/2, and 2 times 1/2 is 1. So instead, we already have to move the points just half the distance up the x-axis. But then we also have to now, in our last step, move them horizontally and vertically according to what h and k tell us to do. H is -3. Remember, always the opposite sign of what you see. That means we have to go 3 steps to the left. But k is -1, so we also have to go 1 step down. So I'm going to take each one of our points, 3 steps to the left and 1 step down. 3 steps to the left, 1 step down. 3 steps to the left, 1 step down. And that will give us our graph that we can now put into our coordinate plane. And our horizontal asymptote also has moved. It has moved down 1 step, and that was based on our k. So the horizontal asymptote is now at y is equal to -1. So in our next example, b is 2/5. So it's a fraction below 1. That means we're going to have a decay function. But let's look at what it is going to look like when we're all done. 2/5 to the power of -1 will flip the fraction. We get 5/2. 2/5 to the power of 0 is 1. And 2/5 to the power of 1 is, again, itself. And here we have our first 3 points. Now let's set up our coordinate plane. And you can guess where I'm setting it up with the x-axis here a little bit further up. So our key points would normally go like this. 1 to the left, 5/2 up, 0 and 1. and 1 to the right, 2/5 up, a little bit less than half. Here they are, but now we're going to have to take into consideration our dilation and our h and k. The dilation is -2, so first of all we're going to be flipping things. -2 means when we multiply everything by -2, we're going to get -10/2, which is -5. We're going to get -2, and we're going to get -4/5. So that would be our points. No shifts considered yet. So at -1, we're going to have -5. 0, we have -2. And at 1, we have -4/5. And now we're going to shift these points. How many steps? 1 step to the right and 3 steps up. So 1 to the right, 3 steps up. 1 to the right, 3 steps up. And 1 to the right, 3 steps up. Where is our horizontal asymptote going to be? Our horizontal asymptote is at y is equal to +3. Right? Let's put that in, that helps us. And now we can graph our exponential function, which will go like this. Alright, so much for this. And now watch the second part of the tutorial where we'll see some practical applications.